Welcome to Tiger Bytes Physics. Brought to you by the one and only Tiger Bytes Physics icon. The fabulous, magnificent, stupendous, all-knowing, all-seeing, Mr. I Can. Hi there, I am the Tiger Bytes icon. I am here to help you master objectives for force and the laws of motion. Here are our objectives for force and the laws of motion. The list includes key math skills we will need to solve problems about force and motion. Pause the presentation. Read these, think about them for a moment, and then continue. Here is a physics problem that illustrates all of our key objectives. If you can understand and explain this problem and then set up and solve others like it, you will have mastered the key objectives. Once upon a time, there was a student, a box of books, a ramp, and a rope. Pause the presentation. Read the problem and set up your problem-solving checklist before proceeding. You will get more out of this presentation if you make the attempt prior to looking ahead. You must find the acceleration of the box up the ramp in meters per second squared. You know some key information. Correct your problem-solving checklist if it does not match this one and then proceed. Note that omega is the angle of the applied force on the rope with respect to the ramp. Theta is the angle of the ramp with the horizontal plane. Before we can solve the problem, we must visualize it. That almost always means we need to draw a diagram of the problem. Start by taking what we know and placing it on the diagram. Note that our original frame of reference uses a coordinate system where the x-axis is parallel to the horizontal plane and the y-axis is perpendicular to the x-axis and horizontal plane. Also note where we drew our angles for theta, the angle of the ramp, and omega, the angle of the applied force relative to the ramp. Pause the presentation, and draw this as your starting point. Make the diagram large. Use a whole sheet of paper. After all, Mr. I Can has reminded you many times that paper is cheap. It is the tuition that is expensive. The applied force is a contact force because we must have contact between the rope and box for the force to affect the box's motion. We also know that gravity, a field force, is also being applied to the box. So, we should add the gravity vector to our diagram. Note that its direction to straight down along our original y-axis. Now let's change our frame of reference to a more convenient one for this problem. We will want our new x-axis to be parallel to the direction of the box's movement along the ramp. In other words, the new x-axis is the surface of the ramp. That would mean our new y-axis would be perpendicular to the ramp. This new frame of reference will make our problem much easier to solve. Now, we can see that our vector for the gravity force is no longer straight along the new y-axis. So, we will want to see if we can identify its components in terms of the new x and y-axis in our new frame of reference. We start by drawing the y component of the gravity force and label it F sub gy. It is in line with our new y-axis and perpendicular to the ramp. We should do the same with the x component of our gravity force. In this case, it has a direction parallel to the ramp. Since the gravity force would want to push the box down the ramp, the direction of F sub gx is down the ramp. Note that we now have a right triangle with the x and y components of gravity as legs and the original gravity force vector as the hypotenuse. We can now determine that the top angle of our new right triangle is equal to theta, which was our original angle of the ramp to the horizontal. How do we know this? Well, it is elementary geometry based upon complementary angles and the fact that all angles of a triangle sum to 180 degrees. Now we will turn our attention to the applied force. That is the force that the student is applying by pulling on the rope at an angle labeled as omega, which is relative to the direction of the ramp. That means that omega is also relative to our new x-axis. The x component of our applied force on the rope is what will actually pull the box up the ramp. It is labeled F sub ax. The y component of our applied force on the rope actually pulls up on the box as if it were trying to lift the box from the ramp. It is labeled F sub ay. Now we have two right triangles, but we are not finished with our diagram. First, we need to draw the vector for the normal force. It is the force exerted against the box by the ramp. It is always exerted at a right angle to the surface. Since we often refer to right angles in math as normal angles, we call the force the normal force, i.e., the force exerted at a right angle to the surface. Our final force for our diagram is the friction force. That is the contact force that is always in the opposite direction of the relative motion between two surfaces. In our case, we are trying to pull the box up the ramp, so our friction force is in the direction opposite that in which we are pulling. Now, this is our diagram that we will use to solve our problem. Pause the presentation and make sure your diagram is complete. If your diagram is sloppy and hard to read, throw it away and make a new one, and yes, keep thinking about that expensive tuition in your future. Now, let's pause and reflect on our objectives for a moment. So far, just by completing our problem-solving checklist and drawing our diagram, we have described how force affects the motion of an object, constructed and begun to interpret our free body diagram, explained the difference between a contact force and a field force, identified some everyday field and contact forces in our problem, and used math skills to diagram a vector problem and select an advantageous frame of reference. Mr. Ican says, great work. Now we can actually use what we have done to solve our problem and determine the acceleration of box up the ramp.